Hi all, here Professor Ravi Kumar, School of Mechanical Engineering, Shastra into the University. I welcome you all to the next lecture today. So today's topic is wind turbine aerodynamics. So here you will be exposed to the working principle of different kind of wind turbines. How do we design the wind turbine? What are the different sub-components of wind turbines and what are the design criteria? With that, we will be closing the discussion for today. So these are the outline of my presentation for today. So we'll be starting with the wind turbine principle. Then we'll go for individual component design like purpose of rotor, blade, and rotor shape, rotor design, and future directions in blade design. So what is basically a wind turbine? So when we talk about a wind turbine is a device that converts the wind's kinetic energy into electrical energy. So wind turbines are manufactured in wide range of sizes with either horizontal or vertical axis. It is estimated that hundreds of thousands of large turbines in installation known as wind farms and now generate over 650 gigawatts of power. So with that 60 gigawatt added each year, so they are increasingly important source of intermittent renewable energy and are used in many countries to lower energy cost and reduce reliance on fossil fuels. As we know that day by day fossil fuels are basically fossil fuel resource sources are depleting and the scientists are forced to look for the method to reuse the energy which is freely available. And as we know that solar and wind energy are basically freely available, which can be utilized to get more and more energy demand. So one study claimed that as of 2020, the wind had the lowest relative greenhouse gas emissions, so the least water consumption demands and the most favorable social impacts compared to photovoltaic, hydro, geothermal, coal and gas. So that's why this is also known as green energy. So a lot of countries are doing a lot of research to effectively utilize the freely wind energy for meeting their annual energy demand. So the smaller wind turbines are used for applications such as battery charging, for auxiliary power, for boats or caravans, and to power traffic or warning signs also. And larger turbines particularly can contribute to domestic power supply while selling unused power back to utility supplier via the electrical grid. So based on the application and demand, we can design the wind turbine as two types, right? Basically, as of now, we know that horizontal axis wind turbine and vertical axis wind turbine. So we look at the brief history of the application of wind turbine. The first use of wind turbine technology was found in Persian age in 7th century and then later on in Europe in 15th century. The wind wheel of Euro Alexandria in 10 AD to 70 AD marks one of the first recorded instances of wind powering a machine in history. So Alexandria basically was a mathematician, an engineer, and who was doing a lot of who has done basically a lot of experimentations on utilization of wind energy into usual work. So, however, the first non-practical wind power plants were built in Sistan, an eastern province of Persia. So this is basically the first recorded, it's official recorded, data which says that the first use was found in Persian is in 7th century. That is now known as Iran. So later on, if we came to the 17th century, tower mills came to the picture, and a lot of advancement happened, and people were utilizing energy for meeting the annual demand. So in the 17th century, tower mills, twistle blade or tapered platform control devices to point to the wind came to the existence. Then 18th century, Dutch bring windmills to US, particularly for pumping the water right from river. On 20th century and now, at current situation, the wind turbines are basically used to generate power, especially in Europe and the rest of the countries. And 2005 onwards, 2% of the total energy demand was meeting with the wind energy. So relatively to other sources, the wind energy conversion basically, or the machine which can convert the wind energy into electrical energy, the relative cost is slightly high, but will go down in future if we will start doing the mass production or mass application of wind turbines for industrial purposes. So this is one pictorial presentation of the three-bladed vertical axis wind turbine, sorry, horizontal axis wind turbine, modern three-bladed wind turbine. The picture is taken from Sandia National Laboratories. So what is the working principle? As I said, that a windmill or wind turbine converts wind energy into rotational energy by means of its blades. Then that rotational energy, that is gone, we can say kinetic energy of the incoming airflow, gets converted into the mechanical energy with the help of a rotary device. Particularly we use a generator, or we use the rotary shaft is connected to a generator to convert into electrical energy. So as a whole, if we say that wind turbine converts wind energy into electrical energy. So what are the various components of wind turbine? If we look at the picture representation of a horizontal axis wind turbine, the horizontal axis wind turbine. So we look at, these are the blades, right, which are attached to the hub. So this is the pitch system, right, and this complete attachment point is known as hub. Right, and these are the blades. This vertical, this pole kind of structure is known as yaw system, about which it can rotate, right? Yaw system, and this is the gearbox, right? Basically, it provides required RPM to your blades, right? Or you can say the blades may be rotating at a very faster rate, but it may be generating. Your generator will be generating power at a some particular RPM. So this gearbox system basically reduce your RPM to the required level or rated level. And this point, right, this is known as main bearing on main shaft, and this is known as the nacelle outer covering. These are the anemometer, particularly attached to anemometer, and here the transformer, and this is generator, right, which will convert your rotational energy into the electrical energy. So these are the various subcomponents of a wind turbine. So if you look at the wind profile, right, across the length of horizontal axis wind turbine, so wind profile will be like parabolic. So this is the vertical tower that we say, vertical tower height, which is also basically designed as for the power output of a wind turbine. And these are the three blades, right, and these are the nacelle, right, outer covering, in which those various subcomponents would be attached. So if we look at the turbine power output versus wind speed, so the wind turbine basically generates the power at some rated wind speed. So this is the variation of power with the wind speed. So the minimum wind speed, right, at which we can have some power generation is nearby 5 meter per second. So any speed below 5 meter per second, your wind turbine will not be generating any power. That is which that point is known as cut-in speed. So immediately after cut-in speed, your wind turbine will start generating the power and keep on increasing, and a point will reach, will get the maximum power generated. It will be constant, and after that stalling will happen. So as per this graph, we can say that wind turbine can generate a maximum power output increase of the wind velocity between 15 to nearby 18 meter per second. So we define like what is the tip speed ratio. Tip speed ratio is nothing but the ratio of turbine tip speed to the wind speed, right? So at what speed your turbine blades are rotating means divided by wind speed is known as the tip speed ratio. So the corresponding to this ratio, the CP is shown in next figure, right? And based on that, the peak efficiency is basically defined how much effectively we can convert the wind energy to the electrical output. So this is turbine power coefficient, right? Our power CP versus tip speed ratio. So if we look at this particular range at which we'll have a maximum turbine power coefficient, so that comes in tip speed nearby 10, right? We are crossing 10, then there's a drastic change in turbine power coefficient, right? So the maximum theoretical efficiency that can be expected from horizontal axis wind turbine is nearby 59.3%, right? And beyond that, uh, there will be no generation, means there will be no proper generation of electrical energy. So, what is the purpose of rotor? So, when we talk about rotor basically is the front part, right, of a turbine. So, the purpose of rotor is to extract energy from the wind and convert that energy to the useful form. So, basically, rotor will enhance the kinetic energy of incoming air. So, this is basically a schematic diagram of a rotor. So, energy is extracted from the wind by decelerating the air through that passes through the rotor. So, it will get decelerated, right? So, this point, right, and this point is called rotor. So, here it will get decelerated initially. Then a wind turbine transforms the kinetic energy immediately after this kinetic energy in the wind to the mechanical energy output in a shaft. And finally, that mechanical energy, that shaft which is rotating, is coupled with a generator where it gets converted into the electrical energy. So this is a pictorial representation of the horizontal axis wind turbine. So this is the tower height, and this is the actuator disc dia. So actuator disc dia is nothing but its propeller when it's rotating is swapping certain area, circular area. That's known as basically the actuator disc diameter. So blade and rotor shape. When we talk about which kind of blades basically being used on wet turbine and the rotor shape. So if we look at this, most of the wind turbine blades may not have same kind of airfoil section throughout the length. So to have a different kind of airfoil section attached along the blade length, right? So like we can have 4-digit series, 6-digit NACA series airfoil at different sections of along the length of wind turbine blade, right, to generate maximum uh, energy out of it. So this is the pictorial presentation of wind turbine blade. So we do usually provide the slightly twist. So these are the different. If we cut it at different locations like 3 and 2 and 1 location, it will have a different kind of pulse shapes, right? So if they're focusing at the tip of blade, it is almost a cambered, right? And yes, slightly thicker portion. If we come at the middle, it is a thicker portion. When coming near the root, right, hub point, it will be much thicker foil section. So corresponding to the thickness, the relative velocity should keep on decreasing. So this is the relative velocity which will generate the one component of lift, right, on this airfoil, which will be assisting in rotating the wind turbine blades. Right. So at different section, it's having different kind of airfoil shapes. So as I said that based on the relative wind direction, it will generate one lift, and one component of that lift will basically assist in rotating the wind turbine blades. And these are the various terminologies of an airfoil already been discussed in previous lectures. So how basically airfoil generates the lift? Airfoil generates the lift based on the pressure difference between top and bottom surface. So top surface is having more curvature compared to the bottom surface. So at top surface, velocity of air will be higher. Alright, so velocity is getting accelerated on top surface, getting decelerated on bottom surface. As a result, there will be negative pressure on top surface and positive pressure on bottom surface. So due to this difference in pressure, there will be a generation of a force perpendicular to the free stream flow direction. That is known as lift. As a basic, what we say, uh, phenomena of generating lift on an airfoil. So as this is the low pressure zone, right? It's high pressure zone. So we look at the low pressure zone that is known as suction side. Right? This is not bottom one is known as a pressure side. Right? Pressure ward or suction side or downwind or windward. So this is windward bottom one and top one is known as a downward side. So real flow scenario, if we look at the boundary layer growth right across the length of the airfoil or length of the airfoil. So initially it is attached. After a certain point, separation will start. So depending on the flow, whether it's a laminar or it's a turbulent, right, your boundary layer profile will be different. So if it is a laminar flow, it will be attached over a certain length, and due to deceleration in the flow velocity, separation starts. But if it's a turbulent, it may attach over a large length of by the chord length of the airfoil, and after that it will detach. So overall, if we look at the drag in laminar flow will be lesser compared to the turbulent flow, right? Turbulent flow, but the stalling will happen in laminar flow much earlier than the turbulent flow. So these are some of the examples of airfoil that we are using in the wind turbine blades, right? Naka 6 digit series is the first example. This is the RISO B115 and FFA W3301. So these are some commonly used, wind airfoil chips, right, in the wind turbine blades. So, what are the targets? Basically, been decided to design an airfoil to be used in a big turbine blade. So, first and most important, target of airfoil design is to get high lift to drag ratio. And second important, this is also very very important. The generation of lift should be insensitive to the roughness on the surface. So, if designing a blade to install a regulated wind turbine, then CL curve should not decrease too steeply after installing, right? So, then only you can have a high CL. And last point, but not least, right? There should not be unwanted noises, right? When flow is getting interacting over the surface of the blade. So reduction of noise is also one of the most important design targets when we're designing the wind turbine blades. And then when we focus on rotor particular design, so basic rotor design, we basically design using blade element momentum method, right? So these are some of the what do we say parameters: blade chord, thickness, and twist distribution. And then overall consideration is rotor solidity and number of blades. How many blades we can use on wind turbine, either three or two. That depends on the power requirements. And these are the major constraints, right? So tape vertices should be lesser and brake rotation should be lesser when we are putting those blades right in operation. An optimum number of blades need to be decided separately, and different rotor designs, right, particularly should be tested to come up with conclusion for optimum rotor design. So this is basically a wind turbine blade profile. If you look at that, so this is basically profile entire thing, and this portion, if we cut it, it is called airfoil. So this is the chord length, or you can say chord. This is called center line, right, running from hub to tip, right. This is a tip. This is called upside. So, or you can say root side and tip side. The tip. This is called leading is right for the airfoil, and trailing is similarly. This is trailing is. This is leading is. This is well known fact. And leeward side, which top surface side, or leeward side, and it's called windward side, bottom one, right? It's called windward side. And this is the east direction, and this is known as left direction for the wind. And this is called torsion or pitch, right? So this basically is a pitch axis. This axis is a pitch axis. It may go like this, right, while it's rotating the pitch axis, and this is a torsional effect. So these are the various terminologies used for a blade. So what are the blade requirements, right? What do we need from our blades? First is low weight. It should be low weight. So reduce loads on rest of the turbine, easier to transport, right, and handle. So it should not be too much heavy. Then transportation problems will be there, as well as your tower that over which you are going to mount those blades. Will also be very very bulky, right? We are using high weight wind turbine blades, so that also we need to take into consideration. Stiff tower strike is a design constant, so need to maintain aerodynamic shapes. So it should not be like flat or rotor blades. Otherwise, a lot of airfoil, which airflow interactions will be there. A lot of disturbance, a lot of airflow disturbance, a lot of drag that may cause structural damage to the tower. It should be stiff enough. Then strength and durability. Avoid material failure, right? Particularly extreme load sensitivity, buckling, performance degradation due to erosion, etc. And last one is aerodynamic design. It should be fully aerodynamically designed blade, easy to manufacture. This is one of the uh, most important criteria, right? It should be easily manufactured in shorter period of time, easily availability, low price. So this low price basically is the from customer endpoint, because customer always look for low price and high strength, blade, but it has to be a compromise situation. How a blade designer should meet the customer demand. So low price is also one of the critical parameter, right? While we are selecting the blade for the wind turbine application. So issues in design blades, right? Blade shape, profile shape, maximum operating lift, noise, right? Noise should be as low as possible, and flow improving and controlling devices. Sometimes additional devices need to be attached on the profile to reduce the air induced drag, right? So blade shape consideration in blade design is high lift production. It's the most important, first and most important point, and low blade height, right? Which should be low. So low noise level and stability, blade tower clearance. So there should be proper clearance from the blade tower. Otherwise, it may create a lot of structural damage to the tower. So practical problems with the blade design install, like particularly reduced track from unusual pitch, more noise. So flap-wise blade vibrations during standstill, edge-wise vibration also may happen during run. Right, so those vibrations need to be isolated with for some isolation mechanism. So if we look at the maximum operating lift, right? So this blue color line is basically the high maximum CL airfoil, and this is the normal airfoil. So normal airfoil that basically being used on aircraft may go up to CL below or nearby 1.4. But for the wind turbine blades, right, we always look for maximum CL production airfoil. So it's going more than 1.6, right? Maximum CL. So issues in designing grade, first is noise. Noise is much important criteria that need to be taken into consideration. So aeroacoustic noise sources, from where it may come from turbulent inflow noises like interaction of blades with atmospheric turbulence, or airfoil self noise, right? Felling is noise, or T vortex formation noise, stall separation noise, laminar boundary layer vortex setting noise, or turbulent boundary layer swelling is noise, or blend trolling is noise, and noise from flow or holes or slates or inclusions. So airfoil is not a solid, kind of profile. So it's a hollow section. So it may also have self noise that need to be in a within limit, right? It's not cross that. We have to take extra care, right, while designing the wind turbine blade. So issues, particularly how to improve the uh, flow control devices. That means how to avoid the unnecessary early installing on the airfoil. So for that, various kind of stall delaying mechanisms are there. Some sort of you know additional protrusion can be made on the top surface of the airfoil. Right, that is called stall strip. This kind of thing is known as stall strip, and this kind of combination, right, is strips, right, is known as vortex generators. So the purpose of both the things is to improve the turbulency on the top surface. When turbulence increases, flow will be attached for a longer period of time because of the adverse mixing of the flow. So there would be direct momentum from the free flow to the top surface. So flow will get basically re-energized if we are putting this kind of extra, mechanism on the top surface of the airfoil. So first design is the stall strip. So it basically reduces the stall induced vibration. Uh, so large dynamic forces, when they are coming, it will reduce particularly. So why we use stall strip to solve vibration issues? It basically decreases the maximum CL. So gradient of CL in post stall area will get decreased. So there will be a gradual decrease in lift. It will not be a steep decrease in lift. When it's a steep decrease in lift, it will have a direct impact on vibrations, right, of the F5. So what are the drawbacks? So these are the drawbacks. Drag increases if placed away from the stagnation points. We need to locate the stagnation point, so it should be kept. This kind of design should be kept very near to the stagnation point, so very near to the leading edge. Second is vertex generator. So vertex generator's purpose is to basically enhance the circulation, right, on the top surface. So that will be kept nearby the aerodynamic center, maybe around 20 to 25% of the chord length behind leading edge with the location of the vertex generator placement. That is increasing the lift, right, and more production at the inner part of the blades. What are the drawbacks? Drag basically will increase depending on position, right? If it's nearest the leading edge, more drag penalty will be there. If it is nearby the aerodynamic center, it's a call optimum design. So high CL max increases the extreme loads on the wind blade. So from structural point of view, it is a drawback, right? So larger aerodynamic loads will be acting on the wind. So we have to decide appropriate location where we can install the vertex generator. So self-induced noise may also be there due to the flow interaction in these cavities, right? So noise issues will also be there that also need to be addressed appropriately. Future direction in rotor design. Future direction is we have to improve power production, right, and reduce noise. This is very important criteria, right, and better shape, right, for structural requirement. Active and passive load control otherwise should also be added with. So for that purpose, various modifications already been tried, and at present also we are trying it. So we are putting this kind of tip a tip is called wing boxes, right, or wing lates sometimes. So this will basically reduce the tip vertices. When tip vertices will reduce, that means uh, unnecessary noise is induced due to the tip vertices will get reduced. So reducing tip losses or winglets can be used. So certain winglets or wingtip designs can be used to reduce the tip losses. So called winglets, right? So it is more beneficial to use a winglet compared to extending the wing depending on several parameters and outcome is not given. So how noise emission is affected by winglets on wind turbine is not well known till now, but definitely a lot of experimentations have been done with the winglets on the wind turbine blades, and there was a significant decrease in the overall noise of the wind turbine. So these are some of the feature directions, right? So that's all for the wind turbine. So if you are having any doubt in the current topic, feel free to write in the comment section, or you can directly reach to me on my WhatsApp number. Thank you very much. With this, the fourth unit is over, and your complete syllabus is covered for the subject aerodynamics for mechanical aerospace engineering. So thanks for your patience for today. See you all in the next class. Have a nice day. Good day.